Welcome to Lecture 10 of Microeconomic Analysis 1 with me, Dr. Craig Webb. Today's lecture is the last lecture where we'll be using the tools of consumer theory, and we'll be looking at measuring consumer welfare. In particular, we'll be looking at the change in consumer welfare that results when the price of a good changes. So if, for example, a price of a good increases, then in some sense we know the consumer is worse off. They can't afford things that they used to be able to afford. For example, how can we measure this? Well, utility numbers, for instance, are derived concepts. So we really need to be measuring this in terms of money. How much worse off is the consumer in terms of money? And we'll develop three measures to do this. The three measures that we will look at today in order to measure the welfare impact of a price change. Today we're going to focus on a price increase, so we'll be talking about how to measure the decrease in consumer welfare in monetary terms, putting a monetary value on that loss of utility. We're going to do this in three ways. The first way is called change in consumer surplus. This is by far the most widely used measure of welfare in economics, and we'll begin to see why, although the second and third techniques that we'll consider, compensating variation and equivalent variation, are in some sense, they have nicer theoretical foundations than consumer surplus. But consumer surplus is a good approximation for measuring the welfare impact of a price change, and it's very easy to calculate. So let's start with consumer surplus. So here I've just drawn a typical Marshallian uncompensated demand function with price on the vertical axis, quantity for good one on the horizontal axis. And I've just drawn a point here which says if the price were £3, then this consumer would demand 5 units of good one. If the price, for example, were £10, then I've drawn this demand function so that the consumer would just demand only 1 unit of good one here. Now we can see that when the consumer is willing to buy 5 units of good one when the price is £3, now the first unit they buy, essentially they would have been willing to pay £10 for that 1 unit. We say the consumer gets a surplus of £7 on this first unit when the price is £3. Surplus is very similar to the idea of profit, and indeed the word producer surplus is sometimes used instead of profit when discussing the theory of the firm in economics. For consumers, we use the word surplus rather than profit. Essentially, they paid less than they would really have been willing to. The consumer would have been happy to pay £10 for 1 unit. He's buying 5, and on that first unit, he makes a surplus of £7. Here I've labelled another unit and just added values to say, well, if the price were £8 in this case, the consumer would have been willing to purchase 2 units. If I would have been willing to pay £8 for 2 units, but I'm only paying £3 for each unit, then on the first unit I'm making a surplus of £7, and on this second unit I'm making a surplus of £5. I could continue going through these surpluses, adding up for each unit. Let's look more generally at a demand function here where I've just labelled the price P1 and a quantity Q1. Now remember, one of our assumptions, which was mathematically convenient, was that these quantities are perfectly divisible, so the consumer can consume any amount they want. So here I've just added what looks like a unit of each good and identified the surplus the consumer receives on each unit they're purchasing, which is essentially adding up each of these areas here. Of course, because these are perfectly divisible, we can sum up these surpluses continuously and take an integral, which would be the area below this demand curve, but above the price. And we call that area a measure of consumer surplus. So in some sense, it's the total consumer surplus that they're receiving, the sum of all the surpluses over every possible amount that they could have bought. They would have been willing to pay more for each of those units, but they only have to pay P1 because the market decides a unit price and you pay the same for every unit of that good. Now let's suppose the price increases from P1 to P1 star. What happens to the consumer surplus in this case? Well, we can see here that it shrinks. The consumer surplus at price P1 star is the area below the demand curve, but above P1 star. Okay, so consumer surplus has shrunk. So in some sense, this captures the idea that the consumer is losing some of their gains or some of the profit that they were getting when the price was so low. So if we identify this change, this purple area, we call the change in consumer surplus, and I put a Greek capital delta, which is the typical notation to denote change, capital delta CS, change in consumer surplus, identified with the price increase from P1 to P1 star. So this measures this area. If I calculate this area, it's measuring how much surplus the consumer is losing when the price changes. And it's measured in terms of money. So it's an amount of money. The loss of consumer profit or consumer surplus is this purple area. Of course, this is the integral of the demand function between 2 points, P1 and P1 star. Now, when you see an integral like this, of course, we know that an integral is the area underneath a demand curve between 2 points, P1 and P1 star. Now, I've drawn this sideways because it's the convention in economics to draw demand functions with price on the vertical axis and quantity on the horizontal axis. So area under the curve in this strange diagram becomes area to the side of the curve. Really, what we've drawn here is an inverse demand function. So inverse demand is it's a useful concept. You'll see a lot used in the next semester, where it tells us essentially the price as a function of quantity demanded. This is really what we're drawing, even though we think of demand, the quantity demanded really being determined by the price. So that's consumer surplus. It's, if you know a demand function, it's very easy to calculate these areas. And in this way, we can give a quick, rough and ready measure of the impact of a price increase. Okay, so the more the price increases, of course, the consumer is losing more and more of their surplus. And this change in consumer surplus puts a monetary value on that. So it's by far the most widely used measure of welfare impact of a price change in economics. Next, we're going to look at two ideas from John Hicks, the idea of compensating variation and equivalent variation. So we'll begin with compensating variation. Now, this is going to be a little more involved in terms of deriving the measure, but hopefully more satisfying as well. It has a more concrete theoretical foundation. So the intuition for this is the following. When the price of a good increases, the consumer cannot achieve the same level of utility that they could initially. So we've seen diagrams like this where the consumer initially demands some bundle. If the price increases, the budget set shrinks in some sense. It pivots inwards, in which case the consumer cannot get onto that original indifference curve anymore because they can't afford to. So we could ask the question, well, how much money do we need to give them to compensate this consumer in order to restore their initial level of utility? Okay, so that they can afford a bundle of goods which is just as good as what they started with. Okay, now in order to answer a question like this, we're going to make extensive use of the expenditure function. And we used this in the last lecture, but let's just remind ourselves now, the expenditure function, which we denoted capital E, which is a function of the price of both goods, P1 and P2, and of a target level of utility, U bar. This tells us the minimum expenditure required when the prices are P1 and P2 to achieve a utility level U bar. Okay, so we're going to make extensive use of that. And now let's go on paper and derive the idea of compensating variation. Okay, so let's have a look at the idea of compensating variation. The basic idea of compensating variation is measuring the amount of money it takes to restore a consumer's utility to its initial level after a price increase. So let's do this in more detail now. So I've prepared a commodity space diagram here, and I've just drawn in a budget line. So initially, we have prices P1, P2, and the consumer has income Y. We know how to interpret this diagram. This line has slope minus P1 over P2. And this point here is Y divided by P1. Okay, and we know this point here is Y divided by P2. So we're already familiar with budget lines. So what happens when the consumer faces this prices and income is they choose their most preferred bundle of goods. So let's denote that by bundle E to denote an equilibrium, a consumer equilibrium bundle. And we know that this is characterized as an interior solution where we have a tangency. So let's just draw a tangency, something like this, with an indifference curve. So this is the consumer's starting point. When they face prices P1, P2, and they have income Y, they choose a bundle E. And let's say that this indifference curve, everywhere, all of the different bundles along this indifference curve generate a utility level. Let's call that U bar. Okay. Now, if we remember the expenditure minimization problem, that was phrased differently. It said, well, if we take U bar, this level of utility, as a target and try to minimize the expenditure required in order to reach this level of utility, U bar, when the prices are P1 and P2, that's the expenditure minimization problem. And you can see here, that would be essentially starting with the budget line of the same slope, or ISO expenditure lines, and until we just reach essentially the same point, or exactly the same point, E. So what I mean by this is that hopefully, building on what we've done previously, I could say that the income that the consumer has is precisely the minimum amount of income that they need when the prices are P1 and P2 in order to achieve utility U bar. That is, their income is equal to the value of the expenditure function, the function which gives us the minimum expenditure required to achieve a level U bar when prices are P1 and P2. So we covered this in the previous lecture, and it's worth just making sure we understand that point. We're going to use expenditure functions extensively in what follows. Okay, so that's kind of our starting point. Now let's imagine there's a price increase. The price of P1 increases to P1 star, holding everything else constant. So P2 stays the same and income Y stays the same. How do we represent that graphically? Well, if we look at this point here, which is Y divided by P2, that of course will stay the same because P1 does not appear there. But this point here, if I spent all of my money on good 1, then I'm going to take my income and divide it by a larger number. So I end up with something smaller. Let's say here. So this point here would be y divided by P1 star. Okay. And if I know 2 points, I can draw the whole budget line. Let's connect these. So here is the budget line after the price increase. And of course, the consumer can no longer afford point E, so they have to choose a new bundle. Let's just draw a point here, which is going to be represented by another tangency. Okay, so let's call that E star. And let's say that E star generates a utility level U bar with a star next to it. So U bar star. Okay. Now, by the same logic as before, I could say, well, when the consumer's income Y in this case is precisely equal to just enough income, the minimum amount of income when the price of good 1 has changed to P1 star, the price of good 2 is still P2, and the target level of utility is now U bar star. Okay, so this is interpreting the diagram in exactly the same way as we interpreted it before. And of course, U bar star is less than U bar. Okay, E star is on a lower indifference curve, which means utility is lower. So what's the idea of compensating variation? Well, essentially, because the consumer's utility has decreased from U bar to U star, what we're going to ask is the question, how much money do we need to give them after the price change? So keeping the price of P1 as P1 star, the price of P2 of good 2 as P2, how much income do I need to give them in order to restore their original level of utility, which was U bar? Okay, so mathematically this would mean their income, the amount of money they currently have, plus an amount that we'll call the compensating variation. So I'm going to give them some compensation after this price increase. And that has to precisely be, well, just enough money at these new prices, P1 star, P2, in order to achieve the level of utility that they enjoyed initially. Okay, so in some sense, I'm compensating the consumer by putting them back on the original indifference curve. Now, I don't need to get them to exactly point E. I just have to get them onto this indifference curve. So what's the cheapest way of doing this? Well, we now have a new marginal rate of transformation, marginal rate of exchange. So this budget line is now steep. So you could see that if I was looking for a tangency on the original indifference curve, let's try and draw this parallel. Okay, so if I draw this new budget line here, where I just have a tangency, let's call that E prime. Well, and this has slope minus P1 star over P2. Well, now we can see that the E prime is the cheapest way, or it's the minimum expenditure bundle when the prices are P1 star and P2 in order to achieve a utility level of U bar, the initial level of utility. Okay. So looking at this diagram, if I took this point here and say, how can I read off the level of income here? Essentially, I'm saying this point, if the consumer took this money and spent it all on good 1, they're essentially Y plus CV, and then divided by P1 star would be precisely what this point here is on the axis. So that gives you one way of finding this amount. And if I know this point here and I know this point here, I can calculate the compensating variation. We could also use our equations that we've developed so far. For example, if I took CV in this case is equal to and then just moved y to the other side, the expenditure function evaluated at the new prices, P2, which gives my original level of utility, minus y, okay? And I know that y, well, I've got two expressions for y, but this is the one that gets used the most and we'll use later. So I could write the compensating variation as the difference between the minimum expenditure at the new prices to achieve the initial level of utility minus the minimum expenditure required at the original prices in order to achieve that initial level of utility. So this is the expression that we will use going forward when we talk about compensating variation, the amount of money it takes after the price change in order to restore a consumer's utility. Now, clearly here I've talked about a price increase, so we needed to give some more money. If I was talking about a price decrease, then compensating variation would be a negative amount. I would be taking money off the consumer. Typically, we just refer to the absolute size and interpret the sign of these measures, compensating variation and what follows, equivalent variation. We just interpret the sign according to the situation. So you could put absolute value around this if you wanted to. So let's go over the idea of compensating variation quickly again. Here I've drawn a diagram with a price increase. The price of good 1 increases from P1 to P1 star, fixing the price of good 2 at P2 and the consumer's income Y. The consumer's optimal bundle changes from bundle E to E star. Now we know the equations for these green and blue budget lines. The green budget line I've denoted here as a set of all of the different Q1 and Q2 combinations, so all the different bundles that satisfy the condition, their expenditure for those bundles is precisely equal to income Y at the original price levels P1, P2. The blue line captures the set of all bundles Q1 and Q2 with the property that the consumer is spending all of their income, but this is using the new price levels P1 star and P2. Here I've labelled the indifference curve on the associated with the original optimal level of utility. So this indifference curve has the equation, well, it's a set of all the different bundles Q1 and Q2 with the property that the utility of those bundles is equal to U bar. So we'll call U bar the initial level of utility. Now we can express the budget line in a different way and say, well, the budget line is all of the bundles Q1 and Q2, where expenditure is precisely equal to the minimum expenditure that the consumer would need in order to achieve utility level U bar at the original prices P1 and P2. Now, when we derived the compensating variation, we were looking for how much income to give the consumer in order to restore their utility to the original level. So here I've drawn another blue line, which is taking the new prices P1 star and P2, and then adding to the consumer's income until they can afford a bundle E prime that is on the original indifference curve with utility U bar. I know the equation for this line. It's all of the different bundles Q1 and Q2, which satisfy the condition, the expenditure to purchase these bundles, using the new prices P1 star and P2, is the consumer's original income Y plus this compensating variation, this extra money we're going to give them to put them back on that original indifference curve in the cheapest way possible. Again, we can rewrite this condition, Y plus CV, would be equal to the expenditure, the minimum expenditure required at the new price level, P1 star and P2, in order to achieve utility U bar. Okay, so taking these together, we get that the compensating variation, which is the difference between how much money you need at the new prices to achieve the original level of utility minus whatever your initial income happened to be. So here CV is the expenditure function evaluated at P1 star, P2 and utility U bar minus your original income. And we know that the original income is the same as the expenditure function evaluated at P1, P2 and U bar. Okay, so that's quickly going over the compensating variation measure derived previously. The next way of measuring the welfare impact of a price change that we will consider is called equivalent variation. Now, to give the intuition for equivalent variation, consider the following. We know that when the price of a good, so good 1, it will be our example. So if the price of good 1 increases, then we cannot achieve the same level as utility as before. Okay, so price increases reduce the achievable level of utility. This is also the same if the price didn't change, but we just took money off the consumer. So if we reduced a consumer's income, clearly they cannot achieve the same level of utility as they could with a larger level of income. So this is the question that the equivalent variation concept answers. It says, well, what reduction in income causes the same harm as a specific price increase? When we say causes the same harm, we mean we know that a specific price increase will reduce utility by a certain amount. If the price didn't change, so we keep the original prices, but just ask, how much income do I take off a consumer to cause the same utility decrease? Well, that is called the equivalent variation. So in some sense, it captures an equivalent damage caused by the price increase purely in terms of a monetary number, which will denote EV. So let's go on to paper and develop this concept more formally. So let's talk about the idea of equivalent variation. Here I've prepared a diagram of a price increase for good 1. And of course, this leads to lower utility. Now, equivalent variation asks the hypothetical question, well, suppose the price didn't change, what loss of income would cause the same reduction in utility? Okay, so it's as if a price increase is the same as losing a certain amount of income. Now let's make this precise. So I've prepared a commodity space diagram here with good 1 on the horizontal axis and good 2 on the vertical axis, the 0 here. And I've just drawn a budget line here, which represents when prices are P1, P2, and income is Y. And I've represented the price increase, P1 to P1 star, as the budget line changing from this line to this line here. So we could just make a note here that this point is Y divided by P1, and this point here is Y divided by P1 star. Okay. I've labelled the bundle E as the initial optimal bundle, and made a note here that the utility of the bundle E is U bar. After the price change, the consumer chooses a different bundle, E star, which generates utility of U bar star. Okay, and U bar star is less than U bar. Okay, so we've seen the price increase in this diagram, and we know that it reduces utility from U bar to U bar star. Okay. As we did in our previous section on compensating variation, I could look at this point, this line here. Now, E star maximizes utility subject to the budget constraint when the price is P1 star, price of good 2 is P2, and income is Y. Similarly, I could look at it in the dual way as the solution to an expenditure minimization problem. So I could write Y is precisely the minimum expenditure required when the price of good 1 is P1 star, and the price of good 2 is P2, and the target level of utility is U bar star. Okay, so that's just interpreting the diagram in a dual way as we've done before. Okay, but this will turn out to be useful next. So how do we capture precisely the idea of equivalent variation? Well, what we're going to say is if the price hadn't changed, so we just had the expenditure required when the price is P1, the price of good 2 is P2, and we want to achieve this new level of utility. Okay, clearly this Y is too much income here because we know that the income Y at these prices can generate a higher level of utility U bar. So this is Y minus something that we call the equivalent variation. Okay, so that's precisely the definition of equivalent variation. We could rearrange this and get equivalent variation in this case is equal to the consumer's initial income minus the expenditure required if the prices had not changed to achieve this new level of utility U bar star. And we know that Y is equal to the precise minimum amount of income or money needed at the new price level to achieve U bar star. So we could write the equivalent variation is equal to the minimum expenditure required at the new price level to achieve U bar star minus the minimum expenditure required at the original price level to achieve this new level of utility. Okay? So compensating variation looked very similar, but it had U bar here and U bar here. Equivalent variation, you could remember, is calculated after utility has changed. So U bar star appears here and U bar star appears here. Okay, so if we just put U bar here and U bar here, we'd get compensating variation. U bar star here and U bar star here gives equivalent variation. How do we represent this on the diagram? Well, essentially we're trying to find at the original price level, so this original price, this is the slope of the budget line minus P1 over P2. So we're trying to minimize the expenditure required to just be on that new indifference curve, that lower indifference curve. So if I draw a tangency like this and label a point here E double prime, okay. Now going from E to E double prime, it's not a Hicks substitution effect, okay. The Hicks substitution effect would be going from E to the E prime from our previous part on compensating variation. Sometimes this is called a Slutsky substitution. The Slutsky substitution effect, which is calculated after the price increase. Okay, so there are other theories about substitution and income effects as well. So here, by reducing the consumer's income from Y to this level, Y minus EV, they are able to choose a bundle E double prime that generates utility U bar star and do that in the cheapest way. So if we look at this, we could read off the value on the axis. This would be Y minus EV divided by, and it wouldn't be P1 star, it would be the original price level P1. Okay? So that's how we could read it on the diagram. And as a formal definition, this is how you would calculate equivalent variation. So let's go over the idea of equivalent variation one more time. So here I've drawn a diagram showing a price increase. The price of good 1 increases from P1 to P1 star, keeping the price of good 2 fixed at P2 and keeping the consumer's income fixed at Y. We know the equations for these budget lines. So in particular, the blue line is the budget line associated with spending all of the consumer spending all of their income after the price increase. So using prices P1 star and P2. this new indifference curve, the lower indifference curve that the consumer can only reach after the price increase, well, the equation for that would be it's a set. So I use these curly braces. It's a set of all of the different bundles, Q1 and Q2, with the property that the utility of those bundles is precisely equal to some number, which we called U bar star. Okay. So we know we could express this blue line in a different way and say, well, everything on this blue line requires an expenditure precisely equal to the smallest expenditure the consumer would need, the smallest amount of money the consumer would need at prices P1 star and P2 in order to achieve utility U bar star. Now, the idea of equivalent variation is to say, well, suppose the price didn't change, but instead the consumer's income were reduced. Now we're looking for an income reduction that in some sense causes the same harm as a price reduction. So here I've drawn a new green line which has slope minus P1 over P2, so the original slope of the budget line, so using the initial prices before the increase, and I've simply reduced the consumer's income until they are just able to afford a bundle that I've labeled E double prime. So this would be the cheapest way, the lowest amount, the cheapest way of getting that level of utility at the original price level. Okay, so the equation for this line would be, well, everything along this line, the Q1 and Q2, has the property that the expenditure required for those bundles is equal to the original level of income minus amounts that we called the equivalent variation. Of course, the equivalent variation, if we look at this diagram, we can see that it's the minimum expenditure required in order to achieve a level of utility U bar star when the prices are P1 and P2. So it's the expenditure function evaluated at P1, P2, the original prices, with the new level of utility U bar star. Combining these, we see that the equivalent variation is equal to the difference between the original income and the amount of income required at the original price level in order to achieve utility U bar star. So it's equal to the expenditure function evaluated at P1 star, P2 and U bar star, minus the expenditure function evaluated at P1, P2 and U bar star. Okay, so it looks very similar to compensating variation, except instead of a target level of utility, the original level of utility U bar, we're not trying to compensate the consumer to get them back on the original indifference curve. We're trying to see what income reduction is equivalent to the price increase that reduced their utility level down to U bar star. So we use U bar star when calculating equivalent variation, the utility that's achievable after the price change. In order to compare compensating variation, change in consumer surplus, and equivalent variation, we can develop a graphical way of doing this based on a result we've seen before. So if we remember that Shepard's lemma from lecture 9, and I promised you that the word lemma means something that's useful, or a small theorem that gets used repeatedly. It said what? It said, well, if we partially differentiate an expenditure function, which is a function of P1, P2, and a target level of utility U bar, if we partially differentiate this with respect to P1, then we get the Hicks demand function, the compensated demand function at P1, P2, and U bar. Okay? So, if we remember a result, the fundamental theorem of calculus, which I've expected that you've seen before, but you at least know the idea that integrals are the anti-derivatives in some sense. Now we're going to treat P2 and U bar as constant, so don't worry about the partial yet. But if I wanted to reverse this, then I'd be taking an integral. So based on this idea, if we remember the definition of compensating variation, we showed that compensating variation, the amount of money required in order to restore utility after a price change, to restore utility to the original level, was the difference between the minimum expenditure required at the new prices, the increased price P1 star, to achieve the original level of utility, minus the expenditure required to achieve utility U bar when prices are P1 and P2. Okay, so this was what we've derived as the value of the compensating variation. And looking at Shepard's lemma, we've got the difference between these two. So using the fundamental theorem of calculus, we know that this difference is in fact the integral of this Hicksian demand function, where I'm taking the value at P1 as the lower bound of the integration and P1 star as the upper, H1, P1, P2, target utility U bar, dP1. Okay? So this is effectively the area underneath the Hicksian compensated demand curve. Okay? That's how we interpret an integral. The area underneath the Hicksian demand curve between the points P1 and P1 star. Now, of course, when we draw diagrams, we draw them with price on the vertical axis and quantity on the horizontal axis. So this won't be the area underneath the integral, the Hicksian curve. It will be the area to the side because we're drawing it the wrong way around. So we'll see that in a second. Similarly, the equivalent variation essentially is the same as compensating variation, except we replace U bar with U bar star in this case. The interpretation was it's an amount of money equivalent in terms of how utility decreases. If we took EV away from a consumer's income, their utility would drop from U bar to U bar star, which is precisely what happens when the price increases from P1 to P1 star. So we know that this is P1 star here, P2, and the target level of utility, U bar star, the new target, minus the minimum expenditure at the original prices to achieve U bar star, the new utility level. Using, again, Shepard's lemma and the fundamental theorem of calculus, the fact that integrals are anti-derivatives, I know that this is the integral from P1 to P1 star of the Hicks demand function, the compensated demand function for good one, when the target level of utility is U bar star. Okay? So this would be the area underneath the Hicks demand compensated demand function associated with the target level of utility U bar star. So let's have a look at some diagrams which show these areas. And remember, we draw them the wrong way around. So rather than the area underneath a Hicks curve, we're drawing with price on the vertical axis. So it's the area to the side between two price levels, which we'll see next. So now we know that the compensating variation can be calculated as the area underneath the Hicks demand function between the original price level and the new price level. Now I've represented on this diagram, and we just have to note that because we draw the diagram the wrong way round with price on the vertical axis, that this integral, rather than being the area underneath the Hicks demand function. Really, I've drawn a picture of the inverse Hicks demand function here. And this integral, this area, is to the side of this, what I've labeled as the Hicks demand function here. Okay, so this represents the case of a normal good. The Hicks demand function is downward sloping and steeper than the Marshallian demand, the uncompensated demand function here. And this blue area, if we calculate that area, we get the value, which is an amount of money, which is the compensating variation. Similarly, for equivalent variation, we can calculate the area underneath the Hicksian demand function, but this time we're using U bar star. So we're looking at a different Hicksian demand function. We're looking at the everywhere along this Hicks demand function, which is orange. All of these points are associated with a target level of utility U bar star, which is lower than U bar. Okay, now if we calculate this area, which I've shaded orange here, you will get the equivalent variation, a result that we derived using Shepard's lemma. Now let's just remind ourselves what change in consumer surplus looked like. It was very simple and probably feels like a long time ago now, but this was simply the area underneath, or to the side in this case, of the Marshallian demand function between the two price levels. So this very simple, easy to calculate area, which we've shaded pink here. So if we want to compare these measures, well, for normal goods, we know that the Hicksian compensated demand function is downward sloping when indifference curves are convex, but more importantly, it's steeper than Marshallian demand. Okay, now why is that? Well, for normal goods, the income effect will further, for instance, if the price decreases, you want to demand more because of the substitution effect, and the income effect is positive, so you demand even more. So Marshallian demand is flatter in this diagram than the Hicksian demand curves. So for normal goods, Hicksian demand curves are steeper than Marshallian demand curves. Now, because of this, we can see here quite clearly that the orange area, the equivalent variation, is the smallest of these welfare measures. So evaluating the impact of the price change P1 to P1 star, the equivalent variation will give the smallest number. The compensating variation will give the largest number, and the consumer surplus, or change in consumer surplus, is sandwiched between the two. Okay, so we have to choose which of these measures to use. We just need to bear in mind what type of good it is when comparing across different measures. For inferior goods, this is a little more difficult to draw, but we know that if good 1 is an inferior good, then the Hicks demand is flatter than Marshallian demand in this diagram. Okay, so it's in this case, the equivalent variation is the associated with this orange curve, H1, P1, P2, U bar star. Well, equivalent variation here would be the blue area plus the pink area plus the orange area. Okay, so it's the largest of these areas. The compensating variation is simply the blue area in this case, so the area under the Hicks demand function associated with the original utility level, U bar. And again, we see that consumer surplus is sandwiched between the two. It's the blue area plus the pink area. Now, okay. I mentioned at the start of the lecture that consumer surplus is probably the most widely used measure of welfare in economics more generally. So why is this? Well, first of all, we've seen that it's much easier to calculate. So uncompensated demand functions, Marshallian demand functions, are easier to observe in the data. To construct a Hicksian demand function, we need more knowledge of preferences, really. We need to remove the income effects in order to get the compensated demand functions. So it's achievable, but the Marshallian demand functions are certainly easier to get hold of from the data. I suppose a second reason might be that, well, equivalent variation and compensating variation both have very convincing theoretical foundations. However, how do we choose between the two? Okay, now we know that they give different amounts, different numbers. Well, in some sense, because we know that consumer surplus is always sandwiched between the two, so for normal goods, compensating variation is the greatest and equivalent variation is the smallest, consumer surplus in the middle. And for inferior goods, equivalent variation is the greatest and compensating variation the smallest. And again, changing consumer surplus is in the middle. In some sense, sticking with changing consumer surplus is a kind of way of walking that middle line without facing the criticism of having to choose the appropriate measure depending on the context. So that might be another reason why changing consumer surplus is so widely used. Finally, we should note that the only reason that equivalent variation, changing consumer surplus, and compensating variation are different, so the only reason that these measures give different answers is because of income effects. So they're factoring out income effects in different ways, or for the case of changing consumer surplus, they're not factoring out income effects at all. So the one case where all of these measures will coincide is for the particular class of preferences where there are zero income effects. So if you have the kind of preferences where the consumer always demands the same amount of a good as their income changes, then in this case, all of the measures will give exactly the same answers. This, we've seen an example in your textbook already, is what's known as quasi-linear utility functions. So for quasi-linear utility functions, consumer surplus, equivalent variation, and compensating variation are all going to give you precisely the same answer because the uncompensated and the compensated demand functions coincide for those preferences. So that concludes our work on consumer theory for this course. In the next 4 lectures, we'll be starting our work on the theory of the firm. Now, consumers and firms meet in markets, and we won't have time to study markets during this semester. The different types of market structures, such as competitive markets, duopolies, monopolies, oligopolies, and so on. This is really the subject of semester 2 of microeconomic analysis. So for us, we'll just be introducing the main players. We already know a lot about consumers. And in the next 4 lectures, we'll be looking at the theory of the firm, the theory of production, and of the firm's costs. So the cost minimization problem, and so on. So lots to look forward to, but even more to look forward to in semester 2 when it all comes together. In the meantime, take care.